Hello, everyone. My name is Alfred, and I'm just gonna give you some background about one of our projects, which was moving an ETL process from a Netezza relational database into Hadoop. And this was done for various reasons, with cost and data sharing being one of them. So we tried many things. So the first thing that we tried was MapReduce. Of course, this was about a year and a half ago. And with MapReduce, what we're trying to do is essentially writing, the almost select group by logic that we were doing in the relational database. So we will have the mapper send the patients over the network, and then based on different keys, the reducer will get the data, and we will perform the analytics such as averages, summations, etc. within the reducer. One of the things that we found out with MapReduce, it was very I/O intensive in terms of network and disk. It was just not able to keep up with the amount of data that we were, pushing through the analytics. So the first thing that we decided to do was maybe move into like a more in-memory processing engine, and at the time Spark seemed to be a very good option. But as soon as we picked up Spark, we quickly realized that it was really not ready to give us what we needed in order for us to meet our production deadlines. So for number one, the API was just not matured enough. Number two, at the time of this writing, Spark documentation was just not very rich, so it was very hard to troubleshoot and find the information that you need to implement all these complex analytics. So we put down Spark, and then we decided to move into Hive. And with Hive, the good thing that came with it was we got that really nice SQL API. So it was very easy for ETL developers coming from relational database to quickly adapt Hive and get up and running on HDFS. But one problem with Hive, as you all know, is it will take you a SQL and translate that into MapReduce. So all those problems that are pointed out about network and disk I/O came back again. So it was fast to code, but it was really slow running. So one of the things that we ended up looking at was Impala. Since we're using Cloudera, Impala was already available out of the box. So we took those same SQLs that we had written in Hive and wrote them in Impala, and we quickly saw performance improvements in the magnitude of even 70 to 80%. And it was like night and day. So we're very excited. We finally found something that will work, give us the rich SQL API that we needed, and we were able to write analytic calculations a lot faster than we did when we tried MapReduce and Spark. All right. From a very high level, this is what our architecture looks like. So our source data is still another Netezza system. We wrote our own Spring-based REST service to communicate with our Uzi workflow. As you all know, as I will talk about this in a later slide, Uzi exposes a REST API for you to communicate with. So you can create your workflows, and then from outside the cluster, you can make REST calls to invoke your workflows. I will show you examples of why that is really powerful. So twice a week, we get data from Netezza. Our REST service is notified. It kicks off our scoop job, which pulls all this data into HDFS. Once the data is in HDFS, let me just touch on this a little bit. As I pointed out, initially we started with the MapReduce and Spark, and consuming the raw files and trying to perform string manipulation and finding out what column meant what in a file was very tedious. So we serialized these files into an Avro schema so that the downstream process will, work against a real object versus dealing with, just raw files. So, but for the sake of this talk, we're going to focus heavily on this bottom portion right here. So once these files are available on HDFS, they're ready to be used immediately with Impala. So what we do is we create our Impala tables out of these files, and now that data is available in our Impala database, and now we can kick off our Impala calculation workflow to perform different calculations and then dump the results onto HDFS. Okay. Once this data is available, what we do is we publish that data by invoking another workflow into our Postgres database, where our UI dashboard will consume that data. Now, the reason why we are publishing this data out is, again, to guarantee the SLA of the UI dashboard users accessing these results. As I should point out, this cluster here is not dedicated to us; it's a multi-tenant cluster. So putting a UI on top of this is just brings a lot of problems in terms of trying to guarantee sub-second response time for users. All right. So I've talked about how we created our Impala tables from the raw files in HDFS. And here I'm going to show you a quick example on how that was done. So here is several examples, but if we just focus on this one for now, you will see that we are creating a table, and we are telling the table, hey, I want you to reference this HDFS location for your data. So as soon as this table is created, all the data in the file is available to be queried on this table. This is very, very easy and I think very sweet. Very minimal work and you are up and running. There are different options that you can specify, of course. So in our case, the fields in the file are terminated by a tab delimiter, so you can specify that. You can also specify what character terminates your line, etc. Right, going back here to the PowerPoint. So now that we created that SQL file, for example, we need to be able to invoke that SQL workflow in an automated way through Uzi. So Uzi actually provides a shell action. So if we go back to the code example here, you'll notice that we have an Uzi action, and we are asking it to use a shell action. And for the shell action, we are telling it to run our SQL file for us. And you can pass in as many different parameters as you may want, okay? And here we are telling it to call shell script, which will, take all those parameters and invoke the workflow. All right, coming back over here. So our workflows are not limited to just Impala, right? We used MapReduce where it made sense. For example, when the user creates, the ETL prompts, on how they want the reports to be aggregated and all that good stuff, that stuff is stored in a relational database. So what we do at the beginning of our job is we pull all that data into HDFS. Once the data is pulled into HDFS, we serialize, all those different elements into an Avro object, which we can later use, in a downstream action to perform different business rules about the ETL that we are running. And I will show you that actually in a second. So if we just jump over here, you'll notice that we have a MapReduce, driver class, and we have multiple mappers that are intaking the different files. And if you go inside one of these mappers, you'll notice it's just grabbing the file and it's writing the file out on the context so that we can later grab it on the reducer side. So if we come back over here and we look at our job driver again, you'll notice that we are telling it that our output type is going to be like an Avro format, and the Avro format is pretty much going to be this object that we have here. One thing to point out when we did our Avro stuff, and everyone should know this, is we did not create this class manually. Instead, what we did is we created an Avro schema to represent the objects across different files, and then through Maven, we were able to instruct Maven at build time to reference our schema and output the generated Java classes in our source main Java package. So coming back over here, you'll notice we're even specifying what package we want the output to go into. All right. So now we can go ahead and look at our reducer class, and what you'll notice, our reducer receives an int writable and an object writable because we are sending multiple objects from the mapper, right? So we are using an object writable, and the object writable pretty much lets you encapsulate any writable object that you would like to put inside and send it over the wire. And then to determine what object we are dealing with, we are pretty much using the visitor pattern right here, right, to decide whether to accept the object, right? So through the visitor pattern, we're able to pretty much map all the different objects that were sent back to the mapper, and run some little business rule. And then after that, we write the Avro file out. Okay. So let me just show you an example of a downstream Java action, for example, that's benefiting from this. So this action needed to get that information. Instead of going through raw files, now we are able to just grab everything from HDFS, and we're dealing with Java objects, right? This is the Avro stuff that we've created. So here you'll notice that we're just pulling it out of HDFS and bringing it back and doing whatever business rule that we need to do with it. In our case, we write out some information that we later create some Impala metadata tables on top of to help us with our calculations. All right. So Impala for the SQL analytics, as I mentioned, we ended up using Impala. One of the things that we found was it was very straightforward. So there was really, the learning curve was very small, and also it pretty much gave us all of the different functions that we needed to do to calculate different metrics that we needed to show on our dashboards. There's a bunch of built-in functions that come out of Impala. So if you look here, for example, you'll notice that you have string functions, you have conditional functions, date functions, mathematical functions. The list goes on. Okay. And then if for some reason the function that you need to implement is not available, you are open to implement your own in Java or C++ and make it available within Impala for consumption. One thing I will point out, if you're going to write your own user-defined function, if you have C++ experience, I will definitely say go ahead and use C++ because it will run a lot faster than Java. Okay, but if all you know is Java, you can still use Java. The performance overhead is not as much, but you will incur a little performance head. All right, so one of the things that we found out as we were publishing data out of HDFS to Postgres, as I showed you here on this architecture diagram, was that the Scoop API was not using the underlying database utility for performing bulk data dump, into the database. So we did some research, and one of the options that was made available to us was to install the PG bulk load RPMs on the cluster, but then the cluster was not going to be supported. As you can imagine, the Hadoop admins were not very happy to hear that. So what I did instead is I went and evolved my own copy API through Java, leveraging the Postgres copy manager, which is just as fast as the PG bulk load. And we went from pushing data using Scoop, pushing 20 million rows in 30 minutes, dropped down to like 30 seconds. So it was a really, really huge win for us. All right. The other thing that we did was we wanted to decouple our workflow orchestration and coordination from the Uzi XML file itself. So instead of creating big workflows or having a workflow with sub workflows and deciding how we are going to invoke things in parallel all within the workflow, instead what we did is we created smaller workflows and decoupled the execution of the workflows outside of the cluster. So we wrote our own metadata-driven REST service, and through this REST service, we were able to invoke different workflows in the cluster. So as I mentioned out, this gave us a great deal of decoupling between workflow definition and workflow orchestration. So a good example is, let's say I'm running 8 workflows in parallel, right? If I decide that 8 workflows in parallel is not really a good idea, instead of touching my workflow to update the fork definition, instead I'll just update a metadata entry in a database table, and I'm done, literally seconds, and I don't have to deploy any code. So with that said, as I pointed out, Uzi provide a rich set of REST API. I will go over one of the most important things that you should know if you're gonna use Uzi in this manner. All right. So number one, whenever you call Uzi, Uzi allows you to put in a property called notification URL. And what that means is when you call Uzi, it's going to reply back to you with the status of the job, whether the job succeeded, whether the job failed, whether the job is running. It gives you that back. So in our case, it was important that we know when the job or the step was completed, so that we can move on and do the next step. So when our REST call is called back here, we run a job post process. I'm not going to get into too much business logic about that, but just so you know, here is where you have the handle to invoke the next job if you want, or mark the job as completed. As you can see, one of the things that it gives you back is the Uzi job ID. the status, whether it was successful or it failed. And also you can inject your own request parameters as you wish. So let's look at how we are submitting our Uzi jobs. So number one, we are doing this through the Spring framework, and we are leveraging the REST template API for submitting this job. Now, with the Spring, you have a lot of flexibility in terms of injecting stuff such as your security information, creating an interceptor and all that good stuff to make sure that if you're communicating to a secured cluster, that you are able to, perform K init and all that good stuff. So here I will just show you, an interceptor where we're injecting the principal, the KRB5 file, pointing to the key tab location on the cluster, and being able to intercept the request. Okay, every time you invoke an action. All right. So coming back to the Uzi workflow submission, one of the things that may be very familiar to you is this class right here. So essentially, what this is similar to your job.properties, or it can be config default.xml. As you notice, is a configuration, and it has many properties within it. So if you open this guy up, you'll be able to inject property name, property value. So what this allows you to do is before you submit your job, in my case, I need to get all of my workflow configuration. So I'm calling my own method here, which grabs whatever I need, okay? Such as the Uzi notification URL, the batch parameter. I'm adding some global parameters into the request, so that I can submit my job to the cluster. So here, what you will notice is I will create the workflow configuration. I will create an HTTP entity, and then I will use the REST template to submit a post to the Uzi URI, okay, with the HTTP entity that I've just created. And that's it. Once I kick that job off, I will get a response back, right? So this gives me a response. And one of the things that I've told Uzi I want to get back is an ID. And this is essentially your workflow ID. All right, so since we used Impala, and one of the things was we needed to do this because Impala is a lot faster than MapReduce, Spark, or anything else to perform the kind of workload that we needed to perform. And the reason why it's a lot faster, as I mentioned, is because it's very memory intensive. Okay, so we have some really good sized nodes for our data nodes. So for example, we have 512 GB of RAM, and since we have multiple workflows and multiple jobs from different teams running Impala, we decided to give Impala 256 GB of that memory, and then we left the rest of the 256 GB memory to yawn for other jobs such as HBase, MapReduce, Spark, etc. So by no means you do not need 512 GB of memory on your nodes to be able to run Impala. But if you want to run many concurrent jobs and you're dealing with a bunch of data and performance is really big thing for you, you will want to invest in memory. All right, so some future consideration here. As I mentioned, we did this project about a year and a half ago, and we tried multiple things. We tried MapReduce, Spark, Hive, and eventually we ended up with Impala. Now, things have changed since we did our project and got it to production. So, for example, Spark has much matured drastically since the last time that we looked at it. So one of the things to consider is maybe before writing any MapReduce, you should definitely look at how you can do that in Spark. The other thing with Impala, the downfall for it, it's not fault tolerant. And what do I mean by that? If you have like a network problem or you have like a disk failure and your job is in the middle of running, Impala does not retry the job on a different node. Okay, instead the job just fails. But if you design your jobs to be broken down into smaller components where they're running really fast, where you don't have things taking a long time to run. As I pointed out, Uzi will call you back and give you like a status of the job. So in our case, we actually built retry logic where we will retry the job several times before marking it as failed. So we're able to implement that, and to be honest, since we've been in production, that logic has only been invoked maybe like 3 times. And because normally in your production environment, you will have a more robust infrastructure where your network is not constantly going down or your disk is not constantly failing. So I just wanted to throw that out there so that that if you are needed to retry the job, there's a way to do it. Impala will not do it for you. The other thing that I'm really excited about, but it's not GA yet, is Hive on Spark. So the reason why we dumped Hive and went straight to Impala, as I mentioned, is because Hive was leveraging MapReduce under the covers, and in turn, it just ended up being slow and even slower than MapReduce. So once Hive on Spark becomes available, we are going to definitely start looking into that, and you should look into that as well. Finally, the last thing that you should actually not the last, right? But another thing you should actually look at is Spark SQL. The last I looked at it, it looked promising. We have not migrated to that yet because, again, the API for SQL, for example, is not as matured as something of Hive or Impala. So we're going to give it a little bit of time, and then eventually we will end up, adapting it. Now, this is not to say that you cannot use it right now. If you have a use case, it's okay to have mixed things such as Impala, Spark, MapReduce, and I showed you that. So you might find in some cases that Spark SQL might just give you whatever you need, or Spark might just give you what you need. So for that particular action, you can write a Spark action, and then you can have that be the input to the next action, which maybe runs Impala or MapReduce or whatever your need may be. Thank you very much.